probabilities, permutations, and combinations today. Basic concepts of probabilities. Here are the topics for today, which is Introduction to Probabilities, Basic Concepts of Probabilities, Multiplication Principle, Permutations, and Combinations. So this is 8.3, which is called Introduction to Probabilities. For that, we have to know some definitions first before we can begin doing some examples. So for example, a random experiment is a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. The sample space, which is denoted by S, is a set of all possible outcomes of a random experiment. Okay, these are examples of sample space. For example, for flipping a coin, right? For flipping a coin once, the sample space is, it can be heads or it can be tails. So the sample space is, the curly brackets means it's a set. It's going to be H, comma, T. H for heads and T for tails. So this is my sample space. For rolling a third die, the sample space is 1, 2, 3, 4, 5, 6. Why is it 1, 2, 3, 4, 5, 6? Because a die has 6 sides, and every side is numbered, has like a little dot or maybe 2. So every side has a 1, a 2, or 3, or 4, or 5, or 6 dots. Okay, now to find the sample space of an experiment, at times it's easier to draw a tree diagram. Okay, let me show you what it means. Example, find the sample space of flipping a coin twice. Here's an example of a tree diagram. So this is your first flip, right? It can be either a heads or it can be either a tails. So after you do the first flip, your second flip, it can be, the first flip might be a heads, and then after that, it can be a heads or it can be a tails. And your first flip was a tails, then after that, it can be a heads or it can be a tails. So with a tree, it's easy, guys. It's more visual because the sample space will be heads, 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 tails, tails, heads, and tails, tails. So this is my sample space. Sample space, right, is denoted by the letter S. S equals to the set of HH, comma, HT, comma, TH, and TT. And again, the H stands for heads and the T stands for tails. Now, an event. An event is an outcome or a set of outcomes of a random experiment. An event is a subset of a sample space. For example, if the sample space for flipping a coin is heads or tails, then one event, the event which stands for E, is equal to a heads, which represents the outcome of heads. Checkpoint. Suppose a die is tossed. Write the given events in the set notation. The number showing is less than 3. Right, so this is my sample space. It can be a 1, 2, 3, 4, 5, 6 for tossing a die. And for A part, the number showing is less than 3. It's going to be the set of 1 and 2, and that's it, right? Because it's saying less than 3. For part B, the number showing is a 5, right? So it's going to be the set of only the element 5. For C, the number showing is an 8. For that one, it's going to be the empty set because there's no 8 on the third die. It's only 1 through 6, so it's going to be the empty space. And D, the number showing is even, right? So from the 1, 2, 3, 4, 5, 6, the even numbers are the 2, the 4, and the 6. That's why there's a set 2, 4, 6. These are examples of the event, of an event to happen. Okay, now, everything that we've done so far leads to basic principles of probabilities, which this is my formula, P of E, which means the probability of the event is equal to the number of the event or the number of the sample space. N of E is the number of elements in the event, and N of S is the number of elements in the sample space. Okay, now, by this definition, the probability of the event is a number that indicates the relative likelihood of the event. Example, This is a checkpoint. Now we're going back to the sample space of rolling a fair die, which can be 1, 2, 3, 4, 5, 6. So now it says give the probability of each of the following events. Event T says the die shows an even number. Right, so there's going to be 3 elements, right? Because the even number of 2, 4, 6 is going to be 3. My sample space is going to be 6. So N of E is 3, and N of S is 6. There's my formula, so it's going to be 3 over 6, which is equal to 1/2. The answer is 1/2. For part B, the die shows a number less than 10. So less than 10 means all the numbers from 1 through 6. So in this case, my N of E is 6, my N of S is 6, so it'll be 6 over 6 is equal to 1. So the probability will be 1 or 100%. For part C, the die shows an 8. Right? There's no 8 on this event, right? Because the sample space is only 1 through 6. It's not there, so there's a 0 element, so the answer will be 0 over 6, which means there's no way you can get an 8 because 8 is not in the set. So the answer will be 0. Here are more examples of probabilities. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen. That's for A part. For B, a diamond. C, a red card, and D, a face card or an ace. I was surprised because I've been going over these in my class, and there's students that they don't know how cards look like because they never play cards, and to me that was kind of surprising. But anyway, that's why like in my classes, I don't like nobody to be left behind, right? So that way I brought the cards here, guys, on the PowerPoint, so that way every student can be aware of how cards look like and also what everything is. For example, there's 4 suits. These are called suits. Okay, 1 suit, 2, 3, and 4. So 4 suits and a deck of cards. The first suit is called the clubs or clovers, which are 13. There's going to be 13 cards for each suit. The second one here, guys, is called spades. There's 13 spades. These are the hearts, suit of hearts, and the suit of diamonds. So you notice there's 13 cards for each suit, which the total will be 52. So 52 cards are total. So this is my sample space, 52. If you notice, there's 26 black cards and 26 red cards. Also, there's 3 face cards. For example, what are face cards? The face cards are the cards that have a face on them. Here an example of face card. This is called a jack, the queen, and the king. Okay, now let's answer these questions here. It says find the probability that the card that you choose is a queen. So my sample space is 52, right? So for it to be a queen, how many queens are there? There's 4 queens because there's 1 queen for each suit. You see the queen of clovers, the queen of spades, the queen of hearts, and the queen of diamonds. So it's going to be 4. And the sample space is 52. So it'll be 4 over 52. You have to reduce it, so the answer will be 1 over 13. That's a probability that if you draw a card, it will be a queen. Now for part B, a diamond. If you notice, guys, we know that from the suits, there's 13 of each suit. So there's 13 diamonds, right? So this will give us 13. There's 13 diamonds on a suit. So 13 is my event. My sample space is 52. So 13 over 52 will give you 1/4. So this is my probability, 1 out of 4. Now for C, a red card. There's 26 red cards and 26 black cards. So 26 red, so it'll be 26 over 52. The answer will be 1/2. Now for part D, the probability that it's a face card or an ace. If we notice, there's 3 face cards for each suit. So there's three diamonds, 3 hearts, 3 spades, and 3 clovers. So 3 times 4 will give us 12. So it's going to be 12 face cards, right? Or an ace. And there's going to be also 4 aces. There's 1 ace for each suit. The ace of diamonds, the ace of hearts, the ace of spades, and the ace of clovers, which means it will be 12 plus 4 over my sample space, which is 52. So it'll be 16 over 52. We reduce it. So it's going to give us 4 over 13. So the chances are for you to choose a face card or an ace, it'll be 4 out of 13. And that's how you do these type of probabilities. Let's do like 2 more examples on probabilities, but now let's do it with dice. This covers number 25 to 28 on page 432, but I believe the page is not correct anymore because this was from the old edition, from the previous edition. I need to update this. Okay, but this is 25 to 28. Okay, now it says find the probability that the sum is 7 or 11. Okay, I mean the sum is not 7 or 11. If you notice, guys, this is equal to 2. This is equal to 3, right? So it's going to be 2 3s. This is 4 and so forth. So not 7 or 11 will be not 7. I mean, first of all, right, 36 is my sample space. Why is 36? Because there's 6 rows and 6 columns. So 6 times 6 is 36. So my sample space for tossing 2 for die will be 36. And right, this is not 7. This is which is 7, and these are 11. Right, so there's 2. Here you can do it 2 ways because I know if it says not 7 or 11, I'm going to add these 2 and subtract it from 36, right? Because it's 36 total, and if you say not 7 or 11, so it means not these nor these, which is 36 minus 8 will give you 28 over 36. And then you reduce it, it's going to give 7 over 9. Or you can do it the other way. The other way is that you're going to omit, you're going to omit the 7, the one that equals to 7 or 11. So you're going to count all the rest. So for example, if you count, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. You see, guys, you get the same answer. But there's more of a chance for you to make mistakes because there's too many to count. That's why I did it this way instead. Okay? Now, let's do one more. On the experiment consisting of rolling 2 for dice and adding the dots on the 2 sides facing up. Find the probability that the sum is less than 4. So less than 4 means it's going to be 3 or less, right? So this is less than 4, and this is less than 4. So the answer will be 3 out of 36. It'll be 112. That's your answer. On these guys, there's a whole bunch of more examples on the, more problems from the book that you guys will do, but with the examples that I'm giving you guys, it's going to help you, get them correctly. Okay. Now let's move on. We're still doing probabilities, but now there's a different circumstance. Example: it says, assume that the probability of couple having a baby boy is the same probability of having a couple having a baby girl. If the couple has 3 children, find the probability that at least 2 of them are girls. Okay. So solution. So at times it's easier to draw a tree diagram. Okay, and I think I did one earlier with heads or tails, but now it's going to be with a boy or a girl. So right, so this is the first birth that they're talking about. The first birth, it can be a boy or it can be a girl. Then for the second birth, if the boy is first, then it can be another boy or a girl. Or if the first birth was a girl, then it can be a boy and a girl. Now this is my third birth. If you had a boy, then after that it can be another boy, or it can be a girl. If it was a boy first and a girl second, then after that it can be a boy or a girl. If the first one was a girl, then a boy, then it can be another boy or another girl. If it was girl, the first two births, after that, it can be a boy or it can be a girl. So here are the possible outcomes. It can be boy, boy, boy. It can be boy, boy, girl. It can be boy, girl, boy. Or it can be boy, girl, girl. Now, if the first one was a girl, it can be girl, boy, boy. Or girl, boy, girl. Or girl, girl, boy. And finally, all of them are girls. Okay, now this is more visual. Now, find the probability that at least two of them are girls. There's 8 total, right? There's 8 different combinations. 1, 2, 3, 4, 5, 6, 7, 8. So my sample space is 8. Now, at least 2 of them are girls means at least 2 of them means 2 or more. Right? So that one's not it. 2 or more. This is my first one. This is my second one. This is my third one. Now, at times, students don't think that all girls is correct, but it's also correct because if it's saying at least 2 of them, it means 2 or more. So also, that one will also be part of my answer. So the answer will be 4, right? So it'll be 4 over 8. The answer is 1/2. That's how it's wise to draw a tree diagram to get these type of problems, because these problems are more visual with a tree diagram. Okay, now this is something from 8.4. Okay, now let's do this. This is also for an example. Okay, it says example 1. Here we're going to be doing the basic concepts of probabilities, the addition rule of probabilities. For any event E and F from a sample space S, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E intersects and F or intercepts F. Okay, solution. Okay, we're going to let R, the set of red, be R, right? Because we're looking for find the probability that the marble will land on a red or even. But before we do that, let's read the example here. It says, when playing American roulette, the croupier, who is the attendant, spins a marble that lands in one of 38 slots in a revolving turntable. The slots are numbered 1 to 36, with 2 additional slots labeled 0 and 00 that are painted green, right? Which are right here, the 00 and the 0 are painted green. Half, this is supposed to be of, not or. Half of the remaining slots are colored red and half are black. In roulette, the slots labeled 00 are not considered even or odd. So now, find the probability that the marble will land on a red or even. So here's my solution, right? So we're going to let R be the red, right? That the marble will land on a red. And I went through the whole roulette table, and I got all the red numbers, right? For example, there's a 1, then the 3, then the 5, right, and so forth. So all these are the ones that are red. Okay, now we're going to let the set of event be E, right, of the even set, right, because it says that the marble will land on a red or even. So we're going to let the E stands for even. These are the even numbers on the table. Again, I went all the way around, and I put all the even numbers with if they're red or black. So for example, 2, 4, 6, 8, 10 are black, 12, 14, 16, 18 are red, 20 to 28 are black, and 30 to 36, but the even numbers are red. So now, so there's my formula. So the probability of red or even is equal to the probability of red, right, plus the probability of even minus the probability where the red intersect the even. And here's the info, right? There were 38 total. There were 18 black, 18 red, 18 even, and 18 odd. So the probability of red, right, is going to be 18, right? And here where it says red and even means where they intersect, right? So they're talking about these right here, what they have in common. You see, they have 1, 2, 3, 4, 5, 6, 7, 8. That's why the number of red intersects E, which is even, is equal to 8. So P of R is going to give you, there's my formula, so it's going to give you what? The red is going to be 18, right? Because there's 18 red, 18 over 38. The even will also be 18 over 38 because there's also 18 even. Now minus the red intersects the even is going to be 8, right? Which is be 1, 2, 3, 4, 5, 6, 7, 8. Minus 8 over 38. So 18 minus 8 is 10. 10 plus 18 is 28. So the answer will be 28 over 38. We reduce it. The answer will be 14 over 19. This example comes from the book. And this is a good way to start because this is a little bit more challenging, but it's always good to put out the info down. And that way make it from a little bit of a complicated problem to something that you guys can do. Okay, break it down and put out the info like I did here. Okay, now, there's another example from the book. Okay, now, it says, suppose that 2 fair dice are rolled. Find each of the given probabilities. The first die shows a 2, or the sum of the result is 6 or 7. Okay, so for part A, right, there's my formula. So I'm going to let A represent the event of the first die is a 2, right? So this is, that'll be the event A. And then I'm going to let event B be the results is 6 or 7. The sum is 6 or 7. Okay, now, here's event A. The event A, right, is in red. Why? Because it says that the first die is a 2, right? So all these have the 2 first. So this is event A. And event B is the sum is 6 or 7, right? So all these have a sum of 6. And then the ones on the bottom have a sum of 7. So, right, so the sample space is 36 because there's 6 rows and 6 columns. So 6 times 6 is 36. Now there's going to be 1, 2, 3, 4, 5, 6 on event A. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 on event B. now, right, so it'll be 6 over 36 plus 11 over 36 minus what do they intersect or what do they have in common, set A and set B. So the intersection will be this one here, so it's going to be 2 of them. There's the first one, there's the second one, so it's going to be 2. 2 over 36. So 6 plus 11 will give us 17, minus 2 will give us 15 over 36. All we do is reduce it, and we got our response. So it'll be 5 over 12. This is my answer, guys. Now, let's do the second part of this example. The sum is 11, or the second die shows a 5. Okay? There's all the possibilities. So again, the sample space is 36. There's my formula. So I'm going to let A represent the event that the sum is 11. So sum is 11 will be these two here on the right. Right, 5 and 6 and C5 equals to 11. So it's going to be 2. I'm going to let B represent the event that the second die is a 5, right? So the second die of 5 will be all these right here. Right, because it's 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, and 6, 5. So it's going to be that right there, which was going to give us 1, 2, 3, 4, 5, 6. So event B will be 6. Now, where do these two events intersect? So the answer will be right here at 6, 5. So it's going to be 1. Now let's fill in the formula. So P of A will be 2 over 36. P of B will be 6 over 36. And P of A intersects B will give us 1 over 36. So the answer will give us 7 over 36. So this is my answer, guys. That's the result. Okay, now, this is called the complement rule for any event. The complement, or means not E, is going to be 1 minus the probability of the event. Or the probability of the event will be 1 minus the probability of the complement. Let me show you a quick example of what they're talking about here. Okay, say the event is that, say today there's a 80% chance of rain, right? That's the event, 80% chance. So what's the event that is not going to rain, right? So it's going to be 1, which will be 100%, which is 1 minus 80%. The answer will be 20%, right? That's an example of what's the complement of, which means not. For example, again, the probability that it will rain is 80%. So then the probability that it's not going to rain will be 20%. That's why it's always 1 minus the event, and vice versa. Okay, now for the second part, odds in favor. The odds in favor of an event E are defined as a ratio of P of E to P of not E, or P complement of E. Right, so this is my formula here, guys. So let me show you guys how we're going to derive to this formula here. Okay, observation. The probability of the event, right, which is a formula, right? For example, the T of E is equal to the number of E over the number of the sample space. The probability of not E, or the complement of E, will be the number of not E over the sample space. If you notice, guys, this is my first fraction on top. The division becomes multiplication, and the second fraction you flip it. If you notice, the sample space cancel. So we get n of E over n of complement of E. You see, guys, there's my formula. So in a simpler way, okay, this is number 27 from page 434. And again, the number is correct, but the page is wrong because now we have a new edition. But this is actually number 27 from the section. It says here, a marble is drawn from a box of 3 yellow, 4 white, and 8 blue marbles. Find the odds in favor in drawing a yellow marble, a blue marble, and a white marble. So for A, odds in favor in drawing a yellow is going to be yellow over not yellow. That's what the formula here on top means. How many are yellow? The answer is 3. Not yellow, the answer is 12. So it'll be 3 over 12, or 1/4, but this is how they want it, right? This is considered an odds. It'll be 1 to 4. These are the odds, which means 1 yellow to is going to be 1 yellow to 4 not yellow. Those are the odds in favor. The odds in favor in drawing a blue. So it's going to be blue over not blue. The blue is going to be 8. Not blue will be 7. So you guys, so in this case, the odds are in favor, right, of drawing a blue more than yellow, because this is going to be 8 blue to 7 not blue. So the odds in favor are real high. For part B, it's going to be 8 to 7. Those are the odds. For part C, odds in favor of drawing a white. This is going to be white over not white. This is going to be for white over 11 not white. So the odds will be 4 to 11. This is in green. That's the answer that they want. Okay. Now, this will assist you for exercises 47 to 54 on page 442. But again, the page is not correct, but those problems are, because it's a new book. It says here, data from the 2016 General Survey can allow us to estimate how many hours people who classified their work status as part-time, full-time, actually worked in the last week. Use the following table to find the probabilities of the events. Okay, for number 47, right? So this is what we're going to be using. The worker is a full-time worker, right? So this is your sample space, 1591. So a full-time worker will be 1271, right? Because these are all the full-time workers. So the total will be 1271. So it's going to be 1271 over 1591. It's going to be like approximately 0.7989. Okay. Number 48, a part-time worker, right? So the probability of a part-time worker is 320. Why? Because part-time worker is 320 over the sample space, which is still 5091. So this will give us approximately 0.2011. Okay, now 49. Work 50 hours or more. Let's see here. So it's going to be right this one here. 50 hours or more will be 393 over the sample space will give us something like approximately 0.2470. For number 50, worked from 0 to 19 hours. 0 to 19 hours, right, is here on the first column here. So it's going to be 106. So it's going to be 106 over the sample space. We do something like approximately 0.0666. Okay. Now let's try number 51. Right, again, same thing as before, that's my sample space. So a part-time worker and someone who worked 40 hours a week. So part-time worker, right, is 320, right? But who worked 40 hours or more. So it's going to be 49, right? The word and means intersection. So it's going to be 49 plus 21 because the first thing we're looking at are part-time workers. And then who worked 40 hours or more, right? It's going to be this column here, which will be 49 because this column here is work 40 to 49 hours. And the 21 means work 50 hours or more. So 40 hours or more is 49 plus 21, which is 70 over 5091. So it's going to be 0.0440. Number 54. A part-time worker. Oh, right. So here's the difference now. This was an and, now this is an or. Who worked 29 hours or less. So here, guys, at times, it's better to use a formula here. Okay? So let's do this. So I'm going to do it both ways. This is without the formula, guys. Why is it this right here, right? Okay, let's do this. Right, so we're going to look at part-time workers, which is this one here. Right? Part-time workers. Or someone who worked 29 hours or less. So these two slots worked 29 hours or less. Okay, so it's going to be the 320 plus the 106 plus the 129. But we subtract these two because these two, I already count them here on the 320, right? So in other words, the 77 and the 87, I cannot count them twice. That's why I subtracted. That's by using the formula here. So then it's going to be, right, so we add that, and here's how we get the answer. They represent the part-timers, part-time workers, right? So this is the part-time workers. And let B represent working 29 hours or less. Okay, now. So the part-time workers are going to be 320, right? Because there's 320 part-time workers. And the ones that work 29 hours or less, it's going to be the 106, right? Because this worked 0 to 19 hours. And the second column worked 20 to 29 hours. So we're going to add these two, 106 plus 129. That's event B. And then where does this event, the part-time workers, and worked 20 hours or less, right, will be this. This is where they intersect. That's what's going to be minus 77 plus 87. That's how we got this right here on the left. So then the answer will be 391. So it'll be 391 over 5091. And the answer will give us something like 0.2458. Okay, now. We can do it, guys, without using the formula. Okay? Here's how. We know that the sample space, right, will be 5091 regardless. That's going to go on as a denominator. Okay, now, like I tell my students, right, since this is first, right, the first thing that they ask is part-time workers. So we're going to have 320 part-time workers. Then we're going to go to those that work 29 hours or less, right, which will be these two columns here. But the 77 and the 87, I don't count it twice. Why? Because they already counted here as part-time workers. So what do I do? What I do, I'm going to add the 320 plus the 29 and the 42, and that'll be my answer. You see, 29 plus 42 plus 320 will give you 391. This is doing it without using the formula. But the formula at times is easier because this way everything is there's more structure and there's more it's more like in order. But you can also do it the other way without the formula. Okay. But anyway, guys, it's up to you what you want to use a formula or just by looking at the chart. And the key word for or means that you're going to write them all down, but you don't repeat them. And you first start with the first one that they're asking for, which is a part-time worker, which was 320. And then you're going to go to the second event, which is 20 hours or less, which would be these two columns here, right? So these are the ones that are being considered. But since the 77 and the 87, they were already counted as a 320 as a part-time workers. That's why we don't count them again. That's why we omit these two, and we just add the 29 plus the 42 plus the 320, which will give us 391. And it'll be 391 over 1591, and this is my result. Okay. Now comes 9.2. 9.2 is called the multiplication principle and permutations and combinations. This is the multiplication principle. It says, suppose n choices must be made with m1 ways to make choice 1, m2 ways to make choice 2, and mn ways to make choice n. So in other words, you're going to multiply the m1 way times m2 times m3 all the way to mn, and that's how many different ways to make the entire sequence of choices. Let me show you an example because the definition is a little bit hard to understand, but with an example, it's going to make more sense. Okay, again, this is number 24 again, but this is, I believe, I just checked today in the class, and it wasn't this one here. It was page 485, but this is number 24. It says, how many different heating cooling units are possible if a homeowner has 3 choices for the efficiency ratings of the furnace, 3 options for the fan speed, and 6 options for the air condenser? Okay, use the multiplication principle. So number of choices for the efficiency ratings is going to be 3. The number of choices for the fan speed is going to be 3, right? 3 options of fan speed. And the number of choices for the air condensers is going to be 6. So it's going to be 3 times 3 times 6, and that's the answer, which will be 54. So there's 54 different ways, different units. Okay. Now this is number 28. It says, the United States Postal Service currently uses 5 digit zip codes in most areas. How many zip codes are possible if there's supposed to be no restrictions? If there are no restrictions on the digits used. And how many will be possible if the first number could not be a 0? So here, guys, there's 2 different questions here. So for the first one is how many different license plates are possible with no restrictions. So it's going to be what? This is my 5-digit zip code. So no restrictions, right? So 10 digits make all the numbers. That means that 10 digits can go in the first slot, 10 in the second, 10 in the third, and the fourth, and the fifth. So we multiply them out, and we get 100,000. Now for part 2, the first digit cannot be a 0, which means there can only be 9 on the first lot, because if the first number cannot be a 0, right? So if we take out the 0, there's only 9 digits left. It's going to be 9, and then 10, 10, 10, and 10. You multiply them out, and the answer is 90,000. Okay, now this is number 30. I believe this is from page 485, not 484. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Remember, for the US, there's 26 letters in the alphabet, and 10 digits make all the numbers. So the first 3, right, are going to be letters. And the second 3 are going to be digits. So here, guys, they're not asking for any restrictions, right? So that means 26 letters can go in the first slot, 26 in the second, 26 in the third. Now 10 digits in the first slot for the digits, and 10 and 10. You multiply it out, you're going to get 17,476,000 different arrangements. Now for part B, when the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. So 3 digits followed by 3 letters. Again, there's no other restriction. So it's going to be 10 times 10 times 10, and 26 times 26 times 26, which will give you the same thing as part A, 17,476,000. Now comes part C. Several years ago, the number described in part B were all used up. The state then issued plates with 1 letter followed by 3 digits and 3 letters. How many new license plates numbers will this arrangement provide? So there's my new letter that they added. Those are my 3 digits and my 3 letters. So that'll be 26 times 10 times 10 times 10 times 26, 26, 26. You multiply it out, guys. Check this out, guys, right? Just by adding 1 new letter to a license plate, look at the big difference that it's going to be. You see, it went up to 456,976,000 possible ways or possible license plates. Imagine, guys, just by adding another letter, it went up, but like 400 and what? Almost 440,000 more. Okay, isn't that amazing? But anyway, guys, that's what we do with these type of problems. Now comes factorial. The n factorial means for any natural number n, the n factorial will be n times n minus 1 times n minus 2, times 3 times 2 times 1. And by definition, 0 factorial is equal to 1. Checkpoint. Evaluate A, 4 factorial, B, 6 factorial, C, 1 factorial, and D, 6 factorial divided by 4 factorial. So for A part, 4 factorial is the same thing as 4 times 3 times 2 times 1. You multiply them out, and you get 24. For B part, 6 factorial be the same thing as 6 times 5 times 4 times 3 times 2 times 1. You multiply them out, you get 720. For C, 1 factorial will just be 1. Now for D part, 6 factorial, yeah, 4 factorial. So 6 factorial will be the same thing as 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Right, so that's equal to 1. That's equal to 1, to 1, and to 1, right? So we have 6 times 5 times 1, which will give us 30. Your answer is 30. And all these can also be put in the calculator. Today, I show my students how to do that. Okay, but you can't put them in the calculator. Now this is called permutations. A permutation of set of an element is an ordering of the elements. For instance, there are 6 permutations orderings of the letters A, B, and C. You have ABC, ACB, BAC, BCA, AAB, and CBA. So there's different orders that you can put 3 letters, A, B, and C. Here, guys, the order matters. For example, ABC and CBA are 2 different orders, even though ABC has all the 3 same letters, but they're in different order. So for permutation, the order matters. Example, how many batting orders are possible for a 9-person baseball team? Okay, so there are 9 possible choices for the first batter, then 8 possible choices for the second batter, and then 7, right, and so forth all the way to get to the 9th batter, which is 1. That's why it's going to be 9 times 8 times 7 all the way to 1, which will give you 362,880 different ways that the lineup can be arranged. Or it can be 9 factorial. It's the same thing. Okay. Now comes permutations. Permutations is NPR. N is a number of elements and taking an R at a time. And here, guys, the order matters. Example, I have 3 letters, A, B, and C. I would like to know how many 2-letter arrangements are possible. Because this one here, guys, I'm going to do it by hand, guys, right? Because I just show 3 letters because it's easy to do with 3 letters, taking 2 at a time. But more than that, it's going to, I mean, it gets a little bit more challenging. Okay? So here it is. So it can be AB, or it can be BA. It can be AC, or CA. It can be BC, or CB. This is my answer, guys. So this is the only way you can arrange 3 letters with using 2 at a time. 6 possible arrangements. Now, how do we use the formula? Right, so the number of elements are going to be 3, and you want to take them at in 2-letter arrangement. So it'll be 3 permutation 2. So it's going to be 3 factorial over 3 minus 2 is 1 factorial. So the answer will be 3 times 2 times 1 over 1. The answer will be 6. You see, guys? And again, this is by seeing, guys, but this is visual, but this is by using the formula. Or you can do it like this, right? And how many 2-letter arrangements? So you're going to put 2 slots here, right? There's my 2-letter arrangements. How many letters can go first? It's going to be 3, right? Because it can be the A, B, or the C. So it's 3. And then if you choose 1, right? How many are left? It's going to be 2. So 3 times 2 is 6. Right? You can do it that way too. Here's an example. From a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people. And how many ways can this be done? So by using the permutation, it's going to be 8 permutation 3. Right, which will give us 8 factorial over 5 factorial, which will give us 8 times 7 times 6 times 5 factorial. The 5 factorials cancel. So we left with 8 times 7 times 6 will give you 336. Or you can do it the other way, right? How many people wanted a soda? So it's 3. So I'm going to put 1, 2, 3. Right? There's 8 different kinds of sodas. So for the first person out of the 3 can select all 8, right? Because there's 8 different types of sodas, so it's going to be 8. Say that one of the sodas was selected, right? One of the different types of soda was selected, then only 7 are left for the second person. And then there's going to be 2 left, right, for the third person, because say this was a Coke and a Pepsi, right? And there's going to be 6 other different ones. So it's going to be 8 times 7 times 6. And if you notice, 8 times 7 times 6 is what we have here on the permutation. Right? You can do it either or. The answer is 336. Now comes the combination. The combination is, for this one, the difference is that order matters. Order does not matter. For permutation, the order matters, and for combination, the order does not matter. Okay, let's go back to the same example with the 3 letters, right? This is the visual part. If the order matters, if the order does not matter, it can be AB, it can be AC, or it can be BC. Because AB and BA is the same thing, right? Order does not matter. So the answer will be 3. Now let's do it by using the formula here. So 3 combination 2 will be 3 factorial divided by 2 factorial times 3 minus 2 factorial. The answer will be 3 factorial over 2 factorial times 1 factorial will give you the same thing as 3 times 2 times 1 and 2 times 1 times 1. You notice the answer will be 3. Okay. Now, this is from the homework. 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? Okay. So again, this is a permutation combination, right? Because order does not matter. So we're going to have 25 and 4. So it's going to be 25 combination 4. Put everything into the formula. So we get 25 factorial over 4 factorial times 21 factorial. We're gonna do 4 times 3 times 2 times 1 factorial for the 4 factorial. And we stop on top, we stop at 21 factorial. This way, it'll be easier to cancel. Those cancel. 4 times 3 times 2 times 1 is the same thing as 24. So we're left with 25 times 23 times 22. The answer will be 12,650. So let me go back real quick. So there's 12,650 ways that the samples can be chosen from. Okay. Now this is the summation of what permutations are. For permutations and combinations, guys, these are the clue words. If it says arrangement, schedule, order, or order matters, it's going to be a permutation. If the problem says group, committee, set, sample, order does not matter, it's going to be a combination. Okay. Now, this is from the lotto. Okay, it says a lottery game requires that you pick 6 different. I forgot to put here the number. 6 different numbers from 1 to 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 numbers if order does not matter? If order does not matter, it's going to be the combination. Right? So it's going to be 99 combination 6, which will give us, what is this? 1,120,529,256. For the second part, how many ways are there to choose 6 numbers if order matters? So that was going to be permutation. For permutation, it will always be more than combination. So this will give us 806 billion. Oh yeah, it was billion, guys. 281,064,220. Now, in exercise 59, it says if you pick 5 out of 6 numbers correctly, you win 5,000. In how many ways can you pick exactly 5 out of 6 winning numbers without regarding to order? That means it's going to be combination. Okay. So here's, first of all, I need to pick 5 out of 6. So 5 out of 6 winning numbers is going to be right from the 6 numbers. I'm going to pick 5 that are correct. It's going to be 6 combination 5. But remember, guys, for the lotto, you need to pick 6 numbers out of 99. So 1 out of, right, so we subtract 99, 6 minus 99, and we live with 93. We subtract 5 out of the 6, right, because that's here, so one is left. So it's going to be 93 combination 1. Right, remember that these, the outer, must, the first numbers must equal to 99, because there's 99 numbers. And the ones to the right, 1 and 6, must equal to the 6. Okay. So we multiply them out. 6 combination 5 will be 6, and 93 combination 1 will be 93. So multiply them out. So you got 558. Okay. Okay. Now, this is the last problem, I believe. It says a financial advisor offers 8 mutual funds in the high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest 3 in high risk, 4 in moderate risk, and 3 in low risk. How many ways can the investor do this? Okay, this is not that complicated, guys. Okay, here's how we do it. Right? If you read the problem carefully, order does not matter, so it's going to be combination. So we start with 8 mutual funds, right? So from 8, we want to choose 3. So it's going to be 8 combination 3. And then we're going to multiply that times, now let's choose from the moderate risk. There's 7 total. And we want to choose 4. So it's going to be times 7 combination 4. Then lastly, right, there's 10 in no risk, but we want to choose 3 of those. So it's going to be 10 combination 3. Right? So that'll be 56. 7 combination 4 will give you 35. And 10 combination 3 will give you 120. You multiply them out. And that's the answer, guys. 235,200 ways it can be done. And I believe this is it for this PowerPoint presentation. I want to thank you for coming today to for Friday Math Happy Hour. Let me go back to the host so they have real important information to share with you guys. Okay.
Thank you very much, Mr. Isasi. Thank you for that wonderful explanation on probabilities, permutations, and combinations. I want to invite everyone to go ahead and join us today at 1 p.m. so that you can join us for the student success presentation. We'll be hosting the EPCC Culinary Arts program at 1 p.m. And also on December the 6th, Happy Math Hour will have Math 1314 and Math 1324, the final exam review. So the success will have how to improve your credit score at 1 p.m. on December the 6th. So we all want to thank you. Remember that next week is Thanksgiving weekend, so we won't have a Happy Math Hour. That's why that gap between today and December the 6th. If you have any questions, go ahead and address them right now. If not, you all have a great weekend. And remember, if you need to review this presentation, go to our YouTube channel and watch it again. Thank you very much.